to meet again. And in today's talk, I will be the moderator of today. I'm Zhang Yi from the School of Integrated Science and Engineering at the University of Electronic Science and Technology of China. I will be the moderator for today. Today is our second talk of the month by Prof. Zhang Shanyong from the Harbin Institute of Technology. In the following 3 weeks, we have another 3 speakers lining up for the talk of this month. In today's talk, we're honored to have Prof. Zhang Shanyong here. Besides me as the moderator, we have 3 panelists today with us. Prof. Zhang Guifeng from the Danish Institute of Advanced Study, Prof. Mao Haiyang from the Institute of Microelectronics and the Chinese Academy of Science, and of course, our founder of iCANX, Prof. Zhang Haixia from Peking University. Next, I would like to invite our speaker of today, Prof. Zhang Shanyong. I'll briefly introduce Prof. Zhang Shanyong. I'm very glad to see Prof. Zhang today, who is my former colleague at the Nanyang Technological University of Singapore. It's been a while since we met last time. Prof. Sam Zhang is a professor now at the Harbin Institute of Technology. He was elected as the fellow of the Institute of Materials, Minerals, and Mining in 2007, the fellow of Royal Society of Chemistry, and the fellow of Thin Film Society, both in 2018. He serves as the editorial board member for the Journal of Material Science and Surface Coating Technology. He is the founding and the current resident of the Thin Film Society. He has published over 400 academic papers with an H-index of 62. Prof. Zhang has been engaged in the preparation and the detection of thin films and coating materials for over 30 years. He has edited over 20 academic monographs published by CSC. His work, Materials Characterization Technology, was adopted as a textbook by nearly 30 top universities and in Europe and America. Prof. Zhang was listed among the top 2 of the global scientists in both 2020 and 2023. Without further ado, let's welcome Prof. Zhang Shanyong to deliver his talk for today. Prof. Zhang, it's all yours.
Okay, thank you very much. Let me share my screen. Can you see the screen?
No, actually, we see your folder on the screen.
The same problem. Yeah, we might be. Yeah, try again.
We got this problem. All right, let me redo it.
It's still your
Now can you
folder.
see?
No, it's still your folder. What we see on the screen is still your folder.
How come? Still folder?
It's unshared. Could you please try sharing it again? No.
Now can you see?
No, still the same screen.
Sam, same problem we met before. I think you should, choose another folder is a screen. Yeah, share the screen, please.
You cannot?
No, same problem. No. What if you close the folder, open the file and close the folder? See if that helps.
Yes,
No, the folder appears again.
cannot, huh?
No, yeah, it's still the folder on the screen. If you can try copy the file to the desktop and close the folder.
Now can you see?
Yeah,
Yeah,
coming.
here we go. Yeah,
Yeah, okay. All
Yeah.
right.
yeah. The floor is yours.
Okay. Sorry about this problem. My name is ZHANG. I'm the president of Thin Film Society. Now I'm a professor at the Harbin Institute of Technology. Before my talk, I'd like to use 2 minutes to talk about my Thin Films conference, which will be held in Singapore in 15 to 19 July 2024. And these are my books where I was in NTU Singapore. And since I came back to China in the first 5 years, I have compiled these 5 books. And now in the pipeline, we have 3-volume set, handbook of perovskite solar cells. And then still in the pipeline, there's another 3-volume set of handbook of advanced energy materials. This set is in Chinese. All right. The talk today I'm going to give is on infrared transmission coupling with mechanical, thermal, and electrical properties. I'd like to thank my team at Harbin Institute of Technology. My team has put their effort to help me prepare this talk. I'd like to mention Dr. Liang, Xu Liangge, Teng Xiangqun, Xu Huaizhi, and Ma Xiaojun. These students did a lot of things for my slides. Okay, with regard to infrared, it's a kind of invisible light to human eyes. Let's first take a look at where it is. This infrared region. Let me get my pointer here. All right. Here we see the whole electromagnetic spectrum, where the visible light is around here, 390 to 780 nanometer in wavelengths. And then over this area is near IR, near infrared region, 0.8 to 1.5 micron, and then followed with medium wave IR, long wave IR, and far IR. Now, then we will have microwave. Yes, that's the microwave oven, the same thing in your kitchen. Followed by that is the radio wave. Now, today we are going to talk about infrared, and for light, we have these properties. What is transparency? We are talking about infrared transparency. This is transparency. When the light comes, you have three kind of response: reflection, absorption, and transmission. If this material is transparent to the light, so the light goes through, of course, these things go simultaneously. And there's another property of the light. Whatever it is absorbed, it will be emitted in the form of radiation. We will get to that later on. So whatever you absorb, it's completely going to be emitted. So the emission equals absorption. So my talk today is on the infrared transmission coupled with mechanical properties, infrared transmission coupled with thermal properties, and the infrared transmission coupled with electrical properties. Why is that? Let's first talk about the transmission coupled with mechanical properties. Here you see when the detector or when the detector on the airplane or whatever flying object, they goes through the air, you will encounter dust form, low temperature or high temperature or high irradiation or whatever. Or even without a dust storm, things like that, you are still going to get this thermal shock. So those you will need protection. First, we talk about the mechanical protection. Besides those things, this thermal shock could also result in buckling of your coating or breakage and detachment. All of these need to be protected. Now, talking about the infrared imaging, let's take a look at these three images. This image is near IR, and this is mid-wave IR. And finally, you have much better resolution at a long-wave IR. That's why we need to increase the long wavelength IR because it gives you much better resolution. Therefore, we have two-folded problem. One way, we need to increase this long wavelength cutoff. To increase this cutoff, we need to increase this mu over u. This mu is the relative atomic mass, and this u is lattice energy. Later on, we will realize that this and this is contradictory because the harness. We have this twofold problem. One is wavelength wants to go longer. One is the harness, the mechanical properties, as we mentioned just now. As you can see here, if you plot the materials in this space, log of lambda wavelength versus the log of mu over u, then you can see that with increase of log mu over u, which is lattice mu over u is the lattice energy. When lattice energy goes down, this mu over u goes up. Therefore, log lambda goes up. I'd like to draw your attention to this material, yttrium oxide film here. Here's yttrium oxide bulk material, and this is the thin film material. We will get to that later on. Now let's draw another space. Lambda versus harness. As you can see, that harness goes up and lambda goes down. Lambda goes down. So that's because just now we mentioned that lattice energy is inversely proportional to lambda. However, lattice energy higher will give you higher harness, which is understandable. Now, in this space, we notice that this lambda here, when lambda equals 12 micron, which is the maximum long wavelength in infrared currently available for particular use. And this gallium arsenide, since we want to increase lambda, and harness of gallium arsenide is also good. See? Then why don't we just directly use gallium arsenide? Now the problem is gallium arsenide has transmission is not satisfactory. All right, so let's remember this. Yttrium oxide has a hardness more than twice that of the zinc sulfate substrate, and a long wavelength limit above 12 micrometers. Now still take a look at this same figure. I highlighted that bulk yttrium oxide is here, and the coating is here. And recently we have moved this property box to this area. What we want eventually is this region, this blue region. The blue region is desired, which is transparent yet hard. We want to move the material or create material into this region. Currently, there is almost no natural materials in this area. So what do? We can either use these existing hard materials like zirconium oxide, ALN, or sapphire, Al2O3, etc., move their lambda up, or use this area's material, push it over this region. So we need a hardness of more than 10 gigapascal, which is necessary condition for long wavelength IR's AR protection. All right. How do we do that? We can do a few things. If you take a look at this diagram, you can realize that lambda varies with thickness. When thickness goes thinner and thinner, you will get transmission better and better. As the thickness of the film increases, the long wave cutoff decreases, which is why thin film have better transparency than bulk material, visible or IR. Now take a look at yttrium oxide thin film. For this, within this transmittance region, which has much better transparency, transmittance than this area. Now take a look at here. This is the for bulk yttrium oxide, and ZNS is here. So within 300 to 1700 nanometer of this range, when you coat yttrium oxide on zinc sulfide, you're actually enhanced your wavelength cutoff from 9.3 to 12 micron. Also, there's another aspect, as we mentioned earlier, that the adhesion of the coating on your substrate. When any coating, when you talk about any coating, the adhesion is a problem. You must have the coating firmly adhere to your substrate. Now, one way of making sure you have a good bond between the film and the coating and the substrate is to use airbag polishing. This could finely adjust the tangential force and the normal force to optimize the coefficient of friction. And by doing that, you are getting your chemical potential down so that you have better collection, adhesion. And there's another, after that, you do another way. making chemical bonding, making a transition layer. So like here you have this ZNS substrate. Eventually you want to make a coating of Y2O3. But if you directly make that, there may not be good. So you need to adjust the precipitation, formulating a transition layer. From ZNS substrate, you first use on ZNS, you have OSY zinc, and then OSY, and then OY, and then finally you have a stoichiometric Y2O3 on the top. Graphically, you can see your coating, your substrate is here, and this area is your transition area, transition region, and finally you have Y2O3. Chemically, you can take a look at this transition from ZNS finally to Y2O3. By this way, you have a good bonding. Now, this is what we desire. Our hardness is doubled from zinc sulfate to over here more than 8, and then for transmittance we increase to over 90%. This is zinc sulfate, which is here, something around 65% transmittance. But when you apply the coating, then we get in this area 3 to 5 region over 90. The highest is 94% transmittance, and over this area 8 to 12, then we get this, which are all above 90%. So we're very glad that a transparent yet hard is obtained. Now next, let's talk about infrared transmission coupled with the thermal properties. This is mainly used in the mid-wavelength infrared region, 3 to 5 micron. Here's the background. When you have a space shuttle or whatever, you need a infrared camera. And this infrared camera, you have a window, like the glass we are wearing. We have a goggle to protect our eyes, right? And but when the flying object flies fast in the air, the friction between the object, between the IR window with the air create heat. And this heat will generate these problems. Structural failure, or even no structural failure, the thermal emission saturation will also make the function failure, which will cause the imaging quality drastically decrease or even completely vanish. As we mentioned before, anything above absolute zero has thermal radiation behavior. And we also mentioned that whatever absorbed must be emitted. So any object, whether it is a stone or dead body or the live things or low life, whatever the emission is unavoidable. The thermal emission, however, we can also make use of it. You can make use of it to do refrigeration, to cool your air, to cool, making hot water for the house, or even making use of the emission to melt materials. Talking about the thermal radiation or emission, we have these 4 laws. For thermal emission, the major part is in the visible light range, which is here. That's why when the sun is up, you feel hot. And even when the sun is down, when you walk on the street, you still feel hot because that is the emission of the absorbed heat. So there is emission energy is proportional to temperature to the quadruple. So it's T to the power of 4, which will increase, that means the emission will increase temperature drastically. Let's remember that we're going to use this formula later on. And this is what we say, whatever absorbed must be emitted. Now, when the emission is going to do bad things to your IR camera, this is what it does. Because this emitting energy is equal to this formula to the power of 4 of temperature. So the temperature quickly rise. When the temperature rise, then you will have a high thermal radiation. This high thermal radiation will blind your infrared detector. What do we do? How to suppress the thermal radiation interference saturation? If the saturation is completely saturated, then you're just been blinded, completely blinded. So what we do? We do this. Within this region, meaning that on top of the infrared cover, you make a functional thin film, which will drastically reduce your thermal radiation. This left image corresponds to this left image, and this right image corresponds to here. When there is a low coating, you get this. When there is a functional film, you get this. So what do we coat? We do a coating. Again, Y2O3, yttrium oxide. This time, we do a coating on sapphire substrate, because for 3 to 5 micron wavelength range, this is what we usually do, what we usually use. Sapphire is Al2O3, which hardness has no problem. but the thermal problem is indeed a big problem. So if we code Y2O3 on sapphire, this is what we have. Take a look at this thermal expansion coefficient, which is in the left figure. Sapphire substrate goes up like this with temperature. And luckily, yttrium oxide coating also goes up with temperature. However, you see, the difference is reducing from low temperatures 33% difference to high temperatures 4% difference. That means when the temperature goes higher, their thermal coefficient meets up, which is very good. Now, take a look at this change of cutoff wavelengths. For the coating, for the sapphire, when temperature increase, there's a drastic reduction. But for the coating, there is almost no reduction. So the difference is also reducing, which is very good. Now let's take a look at the experimental results of yttrium oxide coating on sapphire. Effective reduction of emissivity is observed. You see this dotted line is for the coating. The solid line is for the substrate. With the temperature increase, this difference is obvious. At a higher temperature, without a coating, your emissivity goes up drastically, but still the emissivity of your with coating is very slowly increasing. Finally, take a look at this, which shows from 300 to 600. The upper line is without coating. The lower line is with coating. So obviously with coating, the emission rate greatly reduced, especially at high temperatures. Now with that, you see, without coating, you don't get any image. And with the coating, the image is sharp. Also, we notice that if you want to delay the saturation, if you want to delay the saturation, you can make the coating thicker. Even though from 1 micron to 200 micron, you have only a few seconds delay in the saturation, irradiation saturation, but this few seconds saturation matters a lot. All right, there's another way to get rid of this directional thermal, to get rid of or reduce thermal emission, which is a directional thermal emission. What does that mean? You have to emit, right? But we can make a way to let you emit in a certain angle, and when you're at that angle, then you can see the emission. aside from that angle, you don't have emission at all. Like here, in this 10 degrees, 45 degrees, basically no emission. And when it gets to 72.5, 72.5, 77.5, then you have emission. This can be used in the thermal emission for confidentiality. Like here, if you have this emission of HIT, this image there, emitting light. But if you put it at an angle over this, only at this angle, let's say 45 degrees or 50 degrees, or it only emits in this angle. Then you can see clearly. And for other angle, you don't see, or you don't see clearly. So this is what we call the directional thermal emission. How do we do that? How do we achieve the directional thermal emission? One way of doing this is composite material. You make some materials like this ITO material in the spherical way, and then put it sandwich in something. Or you can make some angular selection by making supersurface on this material. Or you can do gradient epsilon near 0 ENZ coating. This is much easier and much effective, and we're going to do this. Now, what is ENZ material? ENZ materials refers to a material whose real and imaginary part of the dielectric constant approaching 0 in a specific wavelength range. All right, like this material, this oxide material, SiO2, SiO, etc. At these wavelengths, their epsilon or dielectric constant approaches 0. Then at this ENZ wavelengths, the ENZ material of Berryman thickness gives rise to directional emission at a given on-target angle. Let's say using this, let's set this target angle at 80 degrees. And then we can calculate to see that this, for this material, let's say MgO, at this thickness, you will only see the emission at 80 degrees here. At this wavelength, at this angle, you have emission. For hafnium oxide, at hafnium oxide's 14.8 micron wavelength, at 80 degree, then you see the emission, etc. Now, if you want to have a usable coating, you do a series of coatings. For instance, you do a structure of TiO2, of Al2O3, and then you can realize that at a range of wavelengths, not only one wavelength, a range of wavelengths, let's say 8 to 12 micron, you achieve this directional thermal emission. Like here, using this structure, you have this 8 to 12 micron average emission at all angle. Then at the other angles is low, emission is low, only at 80 degrees, which is high. Now, if for other range, like 12 to 16 micron, you still want it to have emission at 80 degrees, you use this kind of structure, Ti2O3, and then TiO2, and then you have this emission emissivity achieved at this range. For this, you have 81 average of 81% emissivity at here, and on other angle, you basically don't see too much. All right, good. Next, let's talk about infrared transparency coupled with the electrical properties. Why we want to do that? Because there's many applications with if you want to stealth, hide this thing, then you want to have transparency together with conductivity. Now, for infrared light to go through, you need non-photon absorption, such as interband or intraband transition. No lattice vibration. That way will give you 100% passing through of your material. However, to make it conductive, you need abundant free carrier distribution and good carrier transport. Obviously, these two are contradictory to each other. From this, you can see, for transparency, you need no electron concentration here. You need, for this to increase, you need no electron concentration. But for conductivity, which is here, you need a high electron concentration. For transparency, you need a high mobility. But for high mobility, you will need lower carrier concentration. However, for conductivity, you need a high carrier concentration. So what do we do? How to solve this problem? Our team has, we have a great team. They are very, they have a very ingenious way of solving this problem by high electric constant. For making this electric constant high, this will give you infrared transparency together with conductivity. And this work was published last year in Light, and is used as a cover article. It's called Far Infrared Transparent Conductors. Now, what's going on? If you want this strong polarization, strong electron polarization, the team actually realized that there is existence of unsaturated bonds when when they do amorphous to crystalline transition, and that give them idea. And then they realize that there is electron deficiency multi-center bonds. So when this increase, when this sigma increase, you have this lambda wavelength increase, which is good. Why there is the high optical dielectric constant? Why it is high? Because of this electron deficiency multi-center. This results in increase of Bohr radius, and that's increase of running away tendency of the electron, which in turn gives rise to strong electron polarization. Like here, this is an octahedral, and if there is each of these each of these atoms, we call it a center. But then, because of this lack of electrons, that's why we call it the electron deficient. Therefore, these electrons will try to take care of all the atoms, so that the radius, Bohr radius of electrons will be increased. When the Bohr radius increase, then the electrons will get further away from the center. Therefore, the attraction is less, and then it's easy to get it polarized. Basically, that is what is going on. And then, in order to realize this multi-center, electron deficient multi-center, we need this principle of three lows: low ionization, low hybridization, and low saturation. Then, with these three satisfied, then you get this electron deficient multi-center. Then we can calculate. Let's use theoretical calculation. Taking a look at this cut off from the table of elements, and examine these materials using these three axes: degree of hybridization, and here's the degree of ionization, and here's the degree of saturation. When you theoretically calculate this, you will find it's easily find that let's say here, if you put this in the two-dimensional, it's easier to see. So here is the degree of saturation, here is the degree of ionization. You want this to be low, of course, you get all these materials. And then our team has realized that in order to get that, you need a certain structure, which is rhombohedral M2N3 structure, which where M are these, N are these elements. And here, another one is cubic. C M1 N1. Here's M. Here's N. And then after theoretical calculation, after those, we can examine the existing materials. These are the materials, traditional materials you can find in the literature. And then calculate according to that. You can you can design our material. These are red. These are the designed materials. From here, you can see that this epsilon, traditionally it is very low. And then here is very high. All these are successful. So finally, we use this to get our work is here and transparent yet conductive. Here's the conductivity. Here's the conductivity. Here is lambda. Your lambda is increasing way over 10, around 15, 16, even to 20 micron. And then you still get high conductivity. Using that theory, then we deposited this material, Bi2 Se 2.4. So the result is over 3 to 5 micron and 8 to 12 micron transmittance is as high as 85 and 98. Over this area is 85, and over this area is over 98. And this is the shielding effect. When it is conductive, then the shielding gets good. So finally, we obtained high epsilon towards high transmittance, yet high conductivity. This is what we obtain. Here is conductivity, here is transmittance, and it goes up from left lower corner to upper right corner. This is exactly what we want to see. So finally, let me summarize what I have talked about. We are talking about infrared transparency. To couple with mechanical properties, to couple with thermal conductivity, to couple with thermal, because we first talk about thermal because it's used in 3 to 5 micron wavelength range, and then that's coupled with thermal properties. And then for mechanical, well, because it is used in long wavelength IR range, we have good mechanical strength coupled with high transmittance, the high transparency. And then finally, with regard to electrical properties, we also coupled electrical properties with transmission. We realize the electrical conductivity with transmittance, with transparency. Thank you very much.
All right, thank you very much, Prof. Zhang. Thank you very much for sharing this very interesting and very impactful work. Next up, let's move on to our panel discussion. We have 3 panel members today. We have 3 panel members today. The first panel member is Prof. Hufei Zhang from the Danish Institute of Advanced Study of Denmark. Prof. Hufei Zhang is a DIS Fellow of Engineering at the Danish Institute of Advanced Study and the head of the Quantum Nanomaterials Group at the University of Southern Denmark. He earned his Bachelor of Science degree from the University of Science and Technology of China in 2004, and his PhD from the Karolinska University Leuven in Belgium in 2013. After that, he joined the Danish Institute of Advanced Study in 2018. Dr. Zhang has long been engaged in the research on quantum nanomaterial and devices with a special focus on exploring and unraveling the emergent quantum phenomenon in lab-grown diamonds. In 2013, Dr. Zhang was elected as the PDM Research Fellow in KU Leuven. In 2014, he was elected as the Scholar of the Belgium Research Foundation. In 2017, he was awarded the Seal of Excellence by the Marie Curie Actions of the European Commission. Right. This is our first panelist. Our next panelist is the Prof. Haiyang Mao. Prof. Haiyang Mao is currently a professor at the Institute of Microelectronics and the Chinese Academy of Science. She received his PhD degree in microelectronics and solid-state electronics from Peking University in 2011. Her research interests include MEMS device and nanomaterial-based sensors. Prof. Mao has published over 70 peer-reviewed journals and has been granted 55 patents, very impressive number. He has also developed several MEMS sensor products, including different types of MEMS thermopiles and other functional molecules, as well as MEMS humidity sensors. These products have been widely utilized in different fields. Well, another panelist of today needs no introduction. This is our founder of iCANX, our Prof. Alice Zhang Haixia from Peking University. Right. Now, I would like to hand the floor to our panelists. And if you have any questions, maybe one question at a time, starting from Prof. Hufei Zhang.
Yeah, Professor Zhang Yi, thank you for the introduction. And before I ask Professor Sam Zhang some questions, I would like to thank Professor Alice Zhang for inviting me to attend this really great seminar. I'm sorry to say this, but to be honest, upon receiving your invitation, I really didn't put much hope on this, but I'm blown away by Professor Sam Zhang's talk today. And first of all, Professor Sam Zhang, that's really a great talk, and not in the sense that your talk is based on very fruitful and successful research results, but also because your talk was given in such a well-organized way so that a layman like myself can learn something from your talk. I think that's the idea of this seminar. And okay, I have several questions, but let me start with a simple one. And as for the first part of your talk about the infrared transmission coupled with mechanical properties of materials, you first talked about thermal shock in harsh environments, and you linked it to the hardness of materials. So basically, you want to create or you want to prepare some samples or some materials which can withstand which can withstand mechanical shocks, but also withstand thermal shock in harsh environment, right?
Yes, both.
Okay.
Yes, we need both.
Yeah. Okay, Professor Zhang Yi, should I ask the next question or should I pass on to?
Or maybe pass on to Prof. Mao first,
Yeah.
and then we'll come back to you.
Yeah.
Okay. Thank you. Thank you for the introduction from Professor Zhang Yi, and thank you for the invitation from Alice. And very nice talk. And Professor Sam Zhang, I have several questions for you. And it seems it is difficult to achieve high surface hardness and at the same time to achieve high optical features, especially with selected wavelength band. So for me, it seems you have developed a protective layer and a protective coating for the instruments involving infrared devices, and with very high transparency. So my first question is, I am quite sorry I didn't quite catch the few slides at the beginning of this talk. So my first question is about in what circumstances the mechanical impulsion can be applied to the the infrared instruments, and in what kind of circumstances mechanical protection shall be needed. So the protective layer should be needed.
I'm not sure I understand your question correctly. You're asking in what kind of environment mechanical protection is necessary?
Yes.
Yeah, okay, let me first answer your question. For mechanical properties, we usually talk about those application in long wavelength area, which is 8 to 12 or even beyond. For those applications, the mechanical behavior is much more necessary. That is because currently, right now, for that kind of areas usage, the substrate of this window, this IR window, is zinc sulfate. Zinc sulfate itself is hardness is a bit low, like around 4. So 4 gigapascal. And therefore, we need to mechanically protect it. But for other applications, like in 3 to 5 micron application area, the substrate usually used is aluminum oxide or sapphire. You know, sapphire's hardness is already very good. So for that, you don't need to protect the from mechanical. However, for that use, you need protection of thermal. So that's why that for that area, we more concentrate on thermal protection.
Okay, thank you.
Yeah.
Thank you.
Sorry, I was on mute. All right, next, Prof. Alice Zhang.
Yes, very wonderful talk, Sam. Yeah, congratulations. I think, yeah. So you always give us some surprise, yeah. In your research in last, many years, I think you keep on going for such wonderful work. Actually, I have a question is about the fabrication. Now you have achieved so high, right? Yeah, the property. So how about the fabrication? Is that can be mass production? Possibly?
Currently, this coatings production, the deposition is that a small laboratory furnace or sputter. But our team or at Harbin Institute of Technology, we have big space which is already obtained. We are making big factory and going to install or some of the systems we can build by hand, build homemade, and then can make production. Because our team leader, Professor ZHANG, he's very concentrated on application. He doesn't buy that when you produce something good, then writing a paper and then shelf it, just put it up. Writing a book, put it there. That's not his style. He's always thinking of making production. So I believe this is in the pipeline.
Okay, great. Actually, as a scientist, a super dream is put your, research not on the bookshop, but also in the production, yeah,
Exactly.
on the market. Yeah. So, congratulations. So, another question is for all these kind of fabrications, even, go to the mass production, go to large areas. The uniformity will be one of the, keywords, right? Yeah. The uniformity for that, did you have any ideas for this? How to, yeah.
Glad, Alice, I'm glad you asked this question. Just I mentioned that homemade facility. Yes, we actually, our team has already made some special instruments, special coder. It's like a dome. It's like a dome. In order to make it, this deposition, not just on the one surface, it's a flat surface, but it's make a dome so that it is curved. Therefore, there is to ensure the uniformity of the whole area.
Wow, super, super nice. Okay, yeah, I pass it through.
Those people at HIT are really ingenious, I have to say. Yeah.
Yeah, it's actually more difficult to put new technology into practice than developing those technologies.
Yes.
Yeah, all right. And back to Prof. Gufei Zhang.
Okay, Professor Sam Zhang, another question from me. And when talking about infrared transmission coupled with mechanical properties of materials, you mentioned something, you showed us data which tells us that the performance of yttrium oxide thin films is much better than that of bulk yttrium oxide bulk. Why is it like that? What's the physical mechanism behind that?
Actually, for thin film, if it is stoichiometric, actually it is, it is good. For thin film, it has low quantity of defects. But for bulk, like yttrium oxide, making it into bulk, it's a ceramic, basically. Then the way of making is usually using the powder mechanical process. Powder and then contained in the container and then press and then center. In this process, you have much more uncertainties, like point defects, even cracks. So that's why the hardness is lower than the thin film. This happens also on other materials. Even in we notice that for high entropy alloy thin films and high entropy alloy bulk material. If you compare that, I have data to show that thin film or coating of high entropy alloy is much higher, 2 or 3 times higher than the bulk. The reason actually is the bulk material has much more deficiencies.
Okay, thank you very much.
Yeah.
All right. Thank Prof. Zhang for the question. And another question from Prof. Mao Haiyang.
Okay, Professor Zhang, I also have a question about the structures of your design. And so what's the thickness of the coating, especially for the multi layers of the coating? So how to design the thickness of the films?
All right. So the question is how to design the structure and how thick or
Yes.
what material to put on. Yes, this is going to be exciting. First of all, what we do is to do the simulation. Use theoretical calculation and then input those materials data into the system and see how first what is the material to put in on each other, and then how thick is each material, because the thickness, as I mentioned, that the thickness determines the transmittance. The thinner, the better in terms of transmission. And then as far as which material we talked about, then we go through its let's say ENZ wavelengths. At each wavelength, at a certain wavelength, this material will emit, and then others will not. So if we want a line of wavelengths at which we all wanted to emit, then we can design one by one and one on top of each other. This one to cover the other one. This one to cover the other one. So that finally we pile this up.
Okay.
And then so which thickness, as we also showed in one of my slide, you at that particular nanometer thickness, you will get that. So that will be the guideline. After we design this, then we go to actual fabrication.
Okay, thank you.
Yeah, good.
Thank you.
Thank you. Thank you very much. Any more questions from Prof. Alice Zhang?
Okay, here. Yeah, maybe this is a question, a little bit out of the technique. So, Sam, I saw you are now in HIT, was in Henan, right? Yeah, this was a new branch.
Yes,
Yeah,
yes.
can you give us some introduction, because that's my hometown. I want to learn more things and new things about there. Yeah, hear something.
Okay, great. Now, let me water. Yeah, actually, HIT, Harbin Institute of Technology, has linked up with Henan Province and Zhengzhou City to establish this HIT Zhengzhou Research Institute. Just a few years ago, let's say the actual setting up of this institute was in the year of 2021, I believe. The year, the year Henan got flood, big flood. That is the year, right? It's 2021 or 2020.
2021.
Yeah, I think it's that year. So that year, the Henan province and especially Zhengzhou city has encountered a big problem financially because of that big flood. Even even in that kind of difficulty, Zhengzhou city and Henan province still put a great effort to support this project. So since then, this was established, and it's in the physical location wise, it's in the eastern part of the city. The railway, not railway, there's a high-speed station in Zhengzhou East Station. When we go to Zhengzhou Research Institute, if we take a high-speed rail, we get off at Zhengzhou East Station. After that, about 15 minutes drive north, you'll get to the research institute. It's by the Longhu, the Dragon Lake. So every morning, basically, I get up doing my walking at that lake. It's just about 1 kilometer away from where I live, and which is also next to the research institute. So next time we come back to Henan, let's meet there.
Yeah.
It sounds like two places are far apart.
Yeah.
Right. Any more questions from Prof. Gufei Zhang?
Yeah, actually, I do.
Yeah.
And another question, Professor Zhang, when you were talking about infrared transmission coupled with thermal properties, you showed us some data that you used superlattice. Well, that's not superlattice, but actually multi-layers of different materials to kind of fill the gaps, like in the thermal properties dependence of infrared transmission. And I'm just wondering whether it's possible to do something similar with the coupling between infrared transmission and mechanical properties of materials, like by using multiple layers. Is this even possible? Because, of course, the lattice mismatch between different layers of materials might give you trouble with the mechanical performance.
Well, first of all, I don't know whether when you talk about the superlattice surface, with regard to directional thermal emission, we didn't do that. That one was cited some other people's work. So what we do is using this ENZ material, piled it up, the multi-layering, so that we designed a structure to make this directional thermal emission. Your question is whether we can couple that with mechanical properties. Yes, I think so. But that you will need to find the oxides which is transparent, and also it has good mechanical properties. For instance, L2O3 or ZrO2. And you find these materials first, and then you find whether they have this ENZ property at a certain wavelengths. In my talk, I only listed a few oxides. Of course, people can search more, or perhaps now you can use AI. You use ChatGPT to help, and then find all the ENZ material, but also notice what kind of wavelengths it has. Meanwhile, the hardness you need. So in this case, that if you do want hardness to come into the equation, each layer you need to plan, needed to plan its hardness and its ENZ wavelengths. And then through calculation, you can calculate what kind of thickness you need. So through those things, you can basically do. But just over the head, what materials have those properties altogether, I don't know. We can check.
Right.
Yeah.
Thank
Sure,
you.
should I
Thank you.
ask?
Yeah, maybe in the
Should I
interest of time, our last question by Prof. Mao.
Okay, thank you. A quick question. I want to know if the surface roughness or surface morphologies will affect the optical features or your multi-layers, and how to,
Yes.
if so, how to control the surface roughness, especially for the near infrared light.
Yeah, this is a very good question. For optical properties, for optical applications, you always want mirror surface. If not completely mirror, you really have to do something well polished. So for deposition, once your substrate is mirror surface, then the deposition will follow. The good thing is we had for optical coatings, the coating thickness, luckily, is just in nanometers. In the nanometers, not like in the mechanical applications, like drilling, the cutting, For those, you need 2 microns thick or even more thicker material. But for optical, you only need a nanometer size. So once you get your substrate flat, mirror flat, so to speak, then your coatings flatness should be okay. And also, during the deposition, your rotation in the system is important. You don't just put your thing stationary. Your substrate, if it's stationary, then perhaps you will get the certain part will be thicker, certain part will be thinner. But if you rotate your substrate, that kind of roughness will be balanced off.
Okay, thank you.
Yeah. Yeah.
Thank you. Thank you. Let's thank the speaker of the day and all the panelists. As a tradition of iCANX talk, we will always hand a certificate to the speaker. But I'm told by Prof. Alice, we will only hand out the speaker if he or she answers the questions to the satisfaction of the audience. Although I couldn't see the feedback from the audience, but I believe the audience are definitely very satisfied and very happy with the talk of today, and more than satisfied with the answers to all the questions raised by the panelists. Can we display the certificate on the backstage? All right, and the certificate is presented to Prof. Sam ZHANG and the Harbin Institute of Technology for his wonderful talk on progress in infrared transparency under Opto Electro Thermo and the mechanical environment. Let's thank Prof. Sam ZHANG. Thank you very much. Yeah.
Okay, thank you very much.
Thank you, thank you. And next, I'd like to promote the iCANX Davos Summit event. It will be held this July from 11th to 12th in Davos, Switzerland. I'm told it's going to be a wonderful event. There will not only be like intensive academic talks and entrepreneurship events, but also a lot of cultural events. Also, there will be an orchestra and a rock band. Not sure if they're going to be if they're going to appear on the stage at the same time, but one way or another, I believe it's going to be a wonderful event. And welcome you all to join this event this July in Davos, Switzerland. And before we end today's session, I'd like to give an announcement of our next week's talk. The talk next week will be given by Prof. Anna Boysen from the Technical University of Denmark. The topic of next week's talk is micro nano engineering and medical devices, which will be hosted by Prof. Christina Nijuas from the University of Twente. And the 3 panelist members are Prof. Liao Yongwen from Westlake University, Prof. Lingqian Chang from Beihang University, and Prof. Xinyu Jiang from the Southern University of Science and Technology. What a panel. I will be definitely joining next week's event, and I hope to see you all there next week. See you next week. Have a wonderful day, wonderful night. See you.
Thank you, Alice.
Okay.
Thank you for
Thanks, Sam. Yeah,
Thank you all.
very good.
Hello, ladies and gentlemen, my dear friends. Welcome to iCANX Davos Summit. So this year we're going to have this big event in Davos, Switzerland. We have 6 topics: innovation, science, technology, investment, management, entrepreneurship. Short for it's time. So it's time for us to go together. It's time for us to all these inspiring talks for the future. We'll have a Nobel laureate firms. We'll have president of academic firms. We'll have president of university firms. All these big names will be here to talk about the future, what's going on for the future. We also invited all these world leaders, scientists, investment management to go together to talk about, what technology and science going to be for the future. And we're going to listen to many sharp talks. All these great figures was from each field. They will share the sharp ideas, the latest results. So it's not only a platform for all these big names, for these shining stars. We also invite you to share your stories. So it's time for you to deliver a talk here. So you are welcome to submit your materials online. So we have many sub-sessions, parallel sessions. You are welcome to submit your materials, and we're going to pick up someone to share that. And it's our time also invite you to be superstars on the stage. If you are college students, welcome to apply for Innovation Award. If you are young scientists, welcome to apply Young Scientist Award. If you already have your startup, welcome to our Startup Award. All these applications is due April 1st, so you have about months to submit it. And it's time for us to go together. We have all these people here who want to work together with you. So we from different continentals, different countries, different areas. So welcome to join us. And it's our time to go to Davos. Now the pre-registration is open now. You are welcome to submit online and go summit together.
在持续发展的社会中，电子元器件需要应对日益复杂化的要求和越来越高的期待。技术革新浪潮汹涌而至，对其高性能的需求、无限小型化的追求，成为行业发展的必然趋势。多层陶瓷电容器、电感器、高可靠性元器件、太阳诱电支撑其全流程的先进技术，提供给用户全方位的服务。为了科技的发展，我们一代代太阳诱电人肩负使命，激情拼搏，以极致的匠心独运，呈现出史诗级作品。研发历程感动了无数电子工程